Hey Wesley, it's me, your crazy grandfather. Boy, have we got something special today. By the way, your mother told me that you were sick, maybe possibly have strep throat, and I hope you feel better soon. Uh, maybe maybe this video will give you something to do for a little while and something to think about. Maybe do some online searching for. This what I'm going to cover today is a little more. It's just one baby step closer to getting involved in some more a bigger understanding of robotics. It's not. I don't want you to think that I'm trying to cover everything. All I want to do is to get some basic concepts out there to you, because you'll hear these concepts. The more you learn, the more you'll hear these concepts, and I don't want you to think that this video is the end all be all of what you're going to need to know about these concepts. It's not. These are I'm just giving you the basic principles, the basic understanding that you can use as a foundation to build on as you go forward. When you get in your higher grades in school, especially in your math classes, you're going to start hearing some of these concepts, because you can consider this a good thing or a bad thing. I'm not really sure. It depends on how you feel about it. But everything involving robotics uses a lot of math. Now, it's not like you have to sit around with a calculator in your hand all the time, because once you start understanding that math, you really don't have to do a lot of formulas. Just every now and then you do, but you do have to know the concepts. You have to know how things fit together. And we're going to talk a little bit about that. We're going to talk a little bit about some actual robotics parts and pieces. And so let's get started. I'm going to reposition the camera, and we'll get started right away. Okay, so let's get started with a basic terminology. There's another word for robotics, and that word is electromechatronics. Now, what this word means is it's actually a German word that's made up of three separate words: electrical, mechanical, and electronics. Now, you've already seen that with the robot arm that I sent you. It had electrical, because you had batteries, you had wires. There were some numbers behind those things to describe voltages and amps and things like that. There was the mechanical, which was the arm itself, the joints, the screws, the gears, the motors. And there was electronics, and that would be the Arduino and the software that's used to drive the Arduino. Now, let's start off with mechanical. Now, there's a couple of concepts that you need to know. You don't have to know them in detail, but you need to understand these concepts about mechanical, and we'll come back to all of these topics later, and we'll fill in some of the blanks. But let's talk about, on mechanical, let's talk about a seesaw. Hey Wesley, I interrupt this video because I was going to try to explain these mechanical principles to you myself, and I found some videos that does a much better job of it, so I'm going to include those now, and we'll look at the a few mechanical things that you're going to need to know, and then we'll come back to the discussion.
A famous ancient Greek once said, "Give me a place to stand and I shall move the earth." But this wasn't some wizard claiming to perform impossible feats. It was the mathematician Archimedes describing the fundamental principle behind the lever. The idea of a person moving such a huge mass on their own might sound like magic, but chances are you've seen it in your everyday life. One of the best examples is something you might recognize from a childhood playground: a teeter-totter, or seesaw. Let's say you and a friend decide to hop on. If you both weigh about the same, you can totter back and forth pretty easily. But what happens if your friend weighs more? Suddenly, you're stuck up in the air. Fortunately, you probably know what to do. Just move back on the seesaw, and down you go. This may seem simple and intuitive, but what you're actually doing is using a lever to lift a weight that would otherwise be too heavy. This lever is one type of what we call simple machines, basic devices that reduce the amount of energy required for a task by cleverly applying the basic laws of physics. Let's take a look at how it works. Every lever consists of three main components: the effort arm, the resistance arm, and the fulcrum. In this case, your weight is the effort force, while your friend's weight provides the resistance force. What Archimedes learned was that there is an important relationship between the magnitudes of these forces and their distances from the fulcrum. The lever is balanced when the product of the effort force and the length of the effort arm equals the product of the resistance force and the length of the resistance arm. This relies on one of the basic laws of physics, which states that work measured in joules is equal to force applied over a distance. A lever can't reduce the amount of work needed to lift something, but it does give you a trade-off. Increase the distance, and you can apply less force. Rather than trying to lift an object directly, the lever makes the job easier by dispersing its weight across the entire length of the effort and resistance arms. So if your friend weighs twice as much as you, you'd need to sit twice as far from the center as him in order to lift him. By the same token, his little sister, whose weight is only a quarter of yours, could lift you by sitting 4 times as far as you. Seesaws may be fun, but the implications and possible uses of levers get much more impressive than that. With a big enough lever, you can lift some pretty heavy things. A person weighing 150 pounds, or 68 kilograms, could use a lever just 3.7 meters long to balance a smart car, or a 10-meter lever to lift a 2.5-ton stone block, like the ones used to build the pyramids. If you wanted to lift the Eiffel Tower, your lever would have to be a bit longer, about 40.6 kilometers. And what about Archimedes' famous boast? Sure, it's hypothetically possible. The Earth weighs 6 times 10 to the 24th power kilograms, and the Moon, that's about 384,400 kilometers away, would make a great fulcrum. So all you'd need to lift the Earth is a lever with a length of about a quadrillion light years, 1.5 billion times the distance to the Andromeda.
No one knows who invented the wheel or when, but we do know that the wheel has become civilization's most valuable servant. Nearly everything we have and use in our everyday lives is brought to us on wheels. And wherever we go, we travel on wheels. Since the very first wheel was used, humans have been inventing new ways to make wheels work for us. For instance, someone discovered that by putting teeth on the rim of the wheel, you open up a whole new range of possible uses for the wheel. We call a toothed wheel a gear. This video will demonstrate how gears can be used to change the direction and speed of their rotation, and how combining different sized gears can increase the amount of force exerted at the rim of the gears. We'll also compare the speed and distance covered by two different sized rolling wheels. And we'll gain a better understanding of how gears and wheels working together are what keeps our world in motion. This example shows how gears change the direction of rotation. When the teeth of these two equally sized gears are meshed together, the gears rotate at the same speed, but in opposite directions. Teeth from the clockwise turning gear on the left push down on the teeth of the meshing gear on the right, causing it to turn counterclockwise. These two gears are the same size, but gears can come in all different sizes. The size of a gear can be measured by its number of teeth, by its circumference, its diameter, or its radius. This gear has 12 teeth. If each tooth is 1 inch wide, then the circumference of the gear is 12 inches long. There are other accurate ways to measure the size of a gear, since we know that the circumference of a circle is pi times the diameter and 2 pi times the radius. The circumference, the diameter, and the radius are all equally good measures of the gear size. When a gear is connected to a power source, like an electric motor or a car engine, it's called the driver gear. The gear to which it's meshed is called the driven gear. In this case, the red 12-tooth gear on the left is the driver gear, and the yellow 24-tooth gear on the right is the driven gear. Because the yellow gear is twice as large as the red gear and has twice as many teeth, it rotates at only half the speed of the 12-tooth driver gear. Since the red driver gear has only half as many teeth as the yellow driven gear, the driver gear must make 2 revolutions to every 1 revolution of the driven gear. If the driver gear is turning at the rate of 10 revolutions per minute, the driven gear will turn at only 5 revolutions per minute. The ratio of the number of revolutions of the driver gear to the number of revolutions of the driven gear is called the gear ratio. Since the 12-tooth red driver gear must rotate twice for every 1 revolution of the 24-tooth yellow driven gear, this represents a 2-to-1 gear ratio. The larger the gear ratio, the slower the driven gear will turn in relation to the driver gear speed. The gear ratio can be changed by changing the size of the gears. In this example, the blue gear with 36 teeth is 3 times larger than the red gear. This gear ratio is 3-to-1. If we want the blue gear to rotate in the same direction as the red gear, we can add an additional gear. Now, this is called a gear train. This gear train consists of 12-tooth, 24-tooth, and 36-tooth gears on 3 axles. As before, the small gear on the left turns twice for each turn of the middle gear, for a 2-to-1 gear ratio. The middle gear turns 1.5 times for each turn of the blue gear on the right, giving a 1.5 gear ratio between the yellow and blue gears. Multiplying the 2 gear ratios together, 2 times 1.5 gives the same 3-to-1 gear ratio as when the red gear meshed directly with the blue gear. So the addition of the yellow gear did not affect the gear ratio, only the direction the blue gear rotates. If direction didn't matter, the yellow gear would be unnecessary. Because gear friction reduces power, engineers never use more gears than are needed. We could get larger gear ratios by adding even larger gears with as many teeth as 48, 6, or even 120. But such large gears can be very cumbersome, and engineers are often limited by space. There's another way of increasing gear ratios, still using reasonable sized gears by teaming them together in pairs. Here are 2 gear pairs we've seen before. On the left is a 12-tooth driver gear meshed with a 24-tooth driven gear. The gear ratio is 2-to-1. On the right is a 12-tooth driver gear meshed with a 36-tooth driven gear. This gear ratio is 3 to 1. If we lock the 24-tooth driven gear to the 12-tooth driver gear on the right, we create a new gear train. The middle axle now has both a 24-tooth driven gear and a 12-tooth driver gear. This type of gear train, where one or more axles has both a driver and a driven gear, is called a compound gear train. What's the gear ratio for this compound gear train? We can find the gear ratio for the compound gear train by multiplying the ratios of the individual gear pairs together, as we did before. The gear ratio of the gear train is 2 to 1 times 3 to 1, or 6 to 1. We can easily check out our math by counting the rotations of the red driver gear of the first pair on the left and comparing that number with the number of rotations of the blue driven gear of the second pair on the right. Whether you use the mathematical formula of multiplying the ratios of the individual gear pairs or count the revolutions of the first and last gears in the train, the overall gear ratio always comes out the same. The overall gear ratio of this gear train is 6 to 1. Gear ratios are determined by both the number of gears used and a combination of their sizes. In this example, still using only 2 pairs of gears, each with a ratio of 3 to 1, we create a compound gear train with an overall ratio of 9. Using various combinations of 12, 24, and 36-tooth gears, gear ratios of 1.5, 2, 3, or any product of these 3 numbers can be produced by simply adding more pairs of gears to the gear train. In this compound gear train, we have ratios of 2 for the first pair on the left, 3 for the middle pair, and 3 for the pair on the right. The overall ratio for this gear train is 2 times 3 times 3, or 18. The material covered so far in this video can be reviewed in the Teacher's Manual for the World in Motion 2, Challenge 2, on the pages listed on the screen. We've seen how gears can be used to change the speed of rotating axles. Next, we'll look at how gears can increase force by comparing them with levers, which also increase force. Even before the wheel was invented, humans learned how to use leverage to help them lift or move heavy objects. We'll start with this 6-foot balance bar with an axle shaft through its center. It's like an empty teeter-totter. The 2 arms of the balance, extending 3 feet on each side of the central shaft, we'll call lever arms. If we hang equal weights from the ends of the lever arms, the teeter-totter is still in perfect balance, since equal force is being applied to the ends of the 2 equal lever arms. But see what happens when we add unequal weight to the ends of the balance bar. The 3-pound weight on the left creates an unequal force that overcomes the 1-pound weight on the right. The unequal force at the ends of the bar is transferred to the shaft in the middle, causing it to twist. This twisting force is called torque, a term that may be new to you. Torque is the amount of twist that's applied to a shaft. It's measured by multiplying the force that's imposed at the end of a lever by the length of the lever arm. With our unbalanced teeter-totter, we see that the counterclockwise torque on the shaft at the left is greater than the clockwise torque on the right, so the difference in torque causes the shaft to twist. How can we balance the torque given these unequal weights? Remember how you balanced a teeter-totter on the playground when your friend was heavier or lighter? As on a teeter-totter, we can move the heavier weight closer to the axle to balance the torque. If we now move the 3-pound weight in to a point 1 foot from the center axle shaft, the bar again comes into perfect balance. The clockwise and counterclockwise torques on the center axle shaft are equal, since the small 1-pound force at the long end of the balance bar is now multiplied by a 3-foot length, or lever arm, while the 3-pound force at the other end is multiplied by only a 1-foot length. It's now clear how we can lift a heavy weight using only a small force. We just need to use a short lever arm for the weight and a long lever arm for our force. The ancient Greek mathematician Archimedes said that with a long enough lever arm, he could move the earth. Such a lever arm would have to be extremely long to generate the tremendous torque required. Keeping in mind that torque is a force times a lever arm, we'll now see how gears can increase torque just as levers do. Think of each tooth on a gear as representing the end of a lever arm that extends from the center of the gear to the tooth. In this example, with the two gears fastened together on a single shaft, the lever arm of each gear is its radius. In the case of gears, the forces at the ends of these lever arms are called rim forces. Just as with the balance bar example, the clockwise and counterclockwise torques on the center axle shaft are equal, since the small 1-pound rim force on the large gear is multiplied by the large gear radius, while the 3-pound rim force on the small gear is multiplied by the small gear radius. While the two torques are equal, the ratio of the rim forces is exactly equal to the gear ratio. This works the same way in meshing gears. Now, to demonstrate how torque is multiplied by meshing gears, we'll use this 3-to-1 ratio as our example. If we place a small weight hanging from the teeth on the left side of the small driver gear, it will produce an equal upward force at the point where the two gears mesh. This upward force, in turn, can be balanced by an equal downward force applied to the teeth of the large driven gear, and the gears will remain stationary. However, the torque in the small gear shaft is balanced by a torque 3 times as big in the large gear shaft, because the lever arm or radius of this gear is 3 times longer than that of the smaller gear. The same formula also applies to gear trains. Whether it's a simple set of 2 gears or a compound gear train, such as this 18-to-1 example made up of several gears, the torque is always multiplied by the overall gear ratio. In this case, the torque in the last driven shaft is 18 times larger than the torque in the driver shaft. Therefore, if the last driven shaft has a gear attached to it with the same lever arm as the driver gear, that is, the small red gear in this example, then the rim force will be 18 times larger. What we've discussed about lever arms, rim force, and torque can be reviewed by referring to the page numbers now on the screen in the Teacher's Manual for the World in Motion 2, Challenge 2. The things we learned about how torque and speed work with gears can also be applied to wheels and how they work. A wheel also has a rim force and a lever arm that corresponds to its radius. And the torque in its axle is again measured by multiplying the rim force by the lever arm. First, to demonstrate a practical application of what we've learned about torque, here we see 2 wheels. One is 3 times larger than the other. In this example, the wheels will drag equal-sized weights. In order to pull the weights, the rim of each wheel must push back against the ground with enough force to overcome the drag of the weight. Let's imagine that both wheels are connected to gear trains which equally apply 1 unit of torque to the axle of each wheel. The small wheel can pull the weight because the force exerted by the rim of the wheel on the ground is enough to overcome the drag of the weight. But with the same torque applied to the larger wheel, because of its 3 times greater size, it has only 1/3 the force at its rim and cannot pull the weight. The large wheel needs 3 times the torque to pull the same weight. When 3 units of torque are applied to both wheels, the smaller wheel is able to pull 3 times more weight than the larger wheel. A good example of this can be seen in bicycles. If 2 bicycles have the same sized gears but different sized wheels, the one with the smaller wheels will be able to climb hills or tow a load with less effort than the one with the larger wheels. Here's another comparison between the same 2 wheels. In one complete revolution, the small wheel will travel only 1/3 as far as the large wheel, because it's only 1/3 the size. In one revolution, Each wheel will travel only the distance equal to its circumference. And if both wheels are turning at the same number of revolutions per minute, the large wheel will travel 3 times faster than the small wheel. This effect of wheel size on the distance and speed a wheel travels is a subject of experiments found in the teacher's manual for the World in Motion 2 Challenge 2 on the pages listed on the screen. Combining the two effects of wheel size on torque and speed that we've discussed, we see that when 2 wheels of different sizes are attached to equal-sized gears driven with the same torque and speed, the larger wheel will travel across the ground faster than the smaller wheel, but will not be able to pull as heavy a load because the force at the rim is less. The two effects are opposite. A bicycle with large wheels can be ridden much faster than one with small wheels because it travels further with each wheel revolution. But the bike with small wheels can more easily climb hills because the force at the rim of its back wheel is greater. Now that we've seen how gears and wheels work, let's look at some of the ways this knowledge is used in the real world. Most electric motors and engines turn at thousands of revolutions per minute, which is much too fast for most applications. By using gears as we've shown, the high rotation speed of a motor or engine shaft can be smoothly reduced to the slower speeds necessary to drive the wheels of a car. This is what a car's transmission does. Higher gear ratios provide the high torque required for acceleration, but lower speed. Lower gear ratios provide higher speed, but lower torque. In these examples, we've seen that in any gear train, the speed of rotation is reduced by the gear ratio, and the torque is multiplied by the gear ratio. The two are always inversely related. If for some application, such as an egg beater, you needed a very high speed with low torque, you could simply reverse the gear train and make the large gear your driver. In this example, you would attach the motor or power source to the large blue gear on the left, making it the driver gear, and the small red gear on the right would become the driven gear, rotating 3 times faster than the driver gear. By simply adding more compound gear pairs, even higher speeds than this can be attained. Gears and wheels are very handy devices. Gears can change the direction of rotation of shafts. They can increase or decrease the speed of rotation or the force exerted at their rims. Wheels can be made to travel fast or slowly across the ground, and can be made to push hard or easily against the ground. With all these possibilities, engineers can design tractors or race cars, clocks and watches, Ferris wheels and rotating restaurants, airplane propellers, and thousands of other useful things that constantly keep our world in motion.
So let's go on ahead and talk about electrical. Now, one thing that I want to say, and I'm very, very serious about this, there's 2 kinds of electricity that we're going to talk about, and I'm only going to mention one of them. And I do not want you messing around with the other one. The one that I do not want you messing around with is the electrical that's in your house voltage. This voltage is dangerous and it will kill you. And I'm not just saying that because I'm some kind of safety Sally. I'm telling you right now, it will kill you. Not only will it kill you, but it'll burn your house down too. This kind of voltage, the kind of voltage that's in your house, is called AC, which stands for alternating current. Now, it's 120 volts, And usually when you see a symbol that's talking about AC, it's going to have some type of a symbol like that. Okay, I can't stress it enough. I want you to stay away from this. Later on, when you get older, when you get some more experience, you get some more training, we'll talk about this and we'll go into detail about it, and we'll learn about some more sophisticated things. But for now, I want you to stay away from it completely. Okay? All right, the other kind of current, the kind of current that you can, or the kind of voltage that you're going to be messing with as you do your robotic stuff, is called DC. And that stands for direct current. Usually it comes in all different kinds of voltages, but usually the symbol that they use to show DC is something like this, or sometimes they just use a straight line. Now batteries, all of your batteries are DC. Now, let's talk about some batteries. You have this type of battery. Let me get it right. You've seen these type of batteries. This type of battery and they have sizes on them that are like AAA, AA, C, D. All of these type batteries are about 1 1/2 volts DC. Okay, I'm going to show you another battery, which I know you've seen. You've seen one of these type batteries before, right? This type battery is 9 volt DC. Now there's lots of other types of batteries. Now I'm going to show you something, and I'm going to throw you a curveball. Do you see this battery pack? You notice on it that it says 7.2 volts. But you also notice that this battery here, let me see. See, it says 9 volts. But this battery says 7.2 volts, but it's a lot bigger. The voltage on this battery is 9 volts, and the voltage on this one is just 7.2. Now, the reason for that, by the way, this battery pack here is a robotics. It's for building robots and stuff. The reason this one is a lower voltage is because it has more power in it. Now, this brings us to a new concept. The new concept is amps. Now, I'm not going to go into a lot of detail about this. I just want you to understand that it exists. So, if I look at this little battery, this is a little bitty battery. It's 1.5 volts, but it has a very small amperage. This battery here is 9 volts, and it has a small amperage. But this battery here is a large battery, low voltage, but it has a high amperage. This thing will deliver a lot of power. Okay? So, we're not going to talk about that a lot today. We'll come back to it because it gets very, very complicated in a hurry. I just want to give you some examples to show you what this means, why it's important to understand volts. Here is a motor, a robotics motor. Now I want to see if I can get the, see if you can see the label on it here. Focus. Maybe you can't, but it says volts, DC 12. So what this is telling me here is that I need 12 volts to run this motor, 12 volts DC. Okay? Now, I'm going to show you one more thing about volts and amps. I want you to think about volts and amps this way. Let's say you have a water hose, and coming out of your water hose you have some water. So volts equals the pressure of this water, but amps equals volume. Okay, that may be too complicated for you, but I think you can understand it. So if I can have a high pressure, if I put my finger over the end of the hose, then I can have a high pressure, but only a little bit of water will come out, so I'll have a low volume. Same thing with small batteries. I can have a high voltage and a low amperage. By the same token, I could take this hose and I could put a great big hose on it, and maybe the water won't squirt out. Maybe it'll just fall out the end. In that case, I would have a low pressure, but a high volume, a high amperage. So in electricity, there's a term to describe this, and you're going to see this term a lot in the future. And this is the last complicated term we're going to talk about today. It's called watts. Now, watts equals volts times amps. So if you look, I'm sure if you look on any of your devices that you have, in your computer, charger, or anything, let me see if I can get that to focus. You will see right here, you'll see input, AC, 120 to 240, and that's where you plug it in the wall with this, with your wall plug. That's your 120. And then it also says, focus. You'll notice here, 0.6 amps. Okay? So if I multiply those together, I'll find out that this thing pulls 72 watts. You'll also see this on light bulbs and things like that. Okay, I hope that didn't give you a headache. It does me, but you know, these are the kind of things that you have to learn before you can really start getting into the good fun stuff. One thing that I forgot to mention about batteries, and I want to mention it now because this is very, very important, is if you'll notice, let's look at this little battery again. You'll notice that on this side it says positive, and on this other side it's sideways. It says negative. So what that means is this terminal is positive and this terminal is negative. All batteries have positive and negative, and it's very, very important that you keep those straight. You're not going to blow anything up, but you may burn up your electronics or your motor or something, or if you hook it up backwards, or maybe your motor will just run backwards. So always remember this: red equals positive, black equals negative. Now I want to illustrate that in a couple of different ways. I want you to, I'm sure you've seen one of these before. I'll turn it on. This is called a multimeter. This one happens to be digital. You can pick one of these up later on when you need one. They're only about, you can even get one for $5. I think I paid $9 for this one. But you'll notice on here, you notice it says DC volts and AC volts. So right now I've got it set on 20 DC volts, and I want to show you something. I want to show you what this does. So I'm going to take this battery. Remember that red is positive here. So I'm going to hook my red up to that. And I'm going to hook my black, which is negative, up to the negative. And I'm going to take a reading on this battery, a voltage reading. And you'll notice it says 9.45 volts. You'll often get, remember this was a 9-volt battery, so you'll often get numbers like that, because usually batteries are a little bit more. Oh, also notice that my battery, or my leads on my voltmeter, notice what color they are: black and red. So red is hot or positive, and black is negative or ground. Okay, and that's another term, is hot and ground for positive and negative. Positive is hot, negative is ground. Okay, so, also on this battery pack, remember this? Notice what color they are: red and black, because it doesn't have any kind of marking on this to tell which one is which, but we know that red is hot, black is ground, or red is positive and black is negative. Okay? Now, let's talk about motors. There's lots of different kinds of motors. The kind of motor that you've seen so far, like was in the kit, the robot arm kit that I sent you, is this type motor. This type motor is called a servo motor. And the reason it is if you'll notice, it has 3 wires: a black, a red, and a white. So what's the black wire? It's negative, right? What's the red wire? It's positive. So your black and your red wire, out of these 2 wires, are the wires that's going to give power to your motor. Now, it's important to understand, before we talk about the white wire, it's important to understand what the purpose of this kind of motor is. This kind of motor is not the kind of motor that you'll plug in and it'll spin round and round like a fan. Okay, this kind of motor it has a lot of power, but it turns very slow, and it only turns a certain amount. Okay, so let's say it's just going to turn 1/2 turn. Well, another way to say 1/2, since one circle has 360 degrees, another way to say one whole turn would be to say 360 degrees. But if I want to say a half a turn, then that would be 180 degrees. And that's what this white wire does. This white wire takes a signal from whatever controller. In your case, what you've got is you've got the Arduino. So it's going to take a signal from the Arduino, and it's going to tell it, and we'll go into it later on what this signal is, but for now we're just going to say that it's some kind of a signal. And that signal on that white wire tells this servo motor how much to turn, how many degrees to turn, and whether it's going forward or reverse. Okay, so that's a servo motor, and that's the motors that you've got in your kit. Now there are other kind of motors. Now if I was making a robot or a car, we'll say, and that motor, I wanted a motor attached to the wheels of my car, well, I wouldn't put this kind of motor on it, because this motor doesn't go round and round and round. I would put a different type motor. This type motor, I may put it on if I had if my car had something that would move an arm like that. Okay, then I would use this kind of motor, because see, it doesn't go round and round. It just moves that much. Okay? Now, another kind of motor, and I showed you one of these earlier, is this type motor here. Some people call these servo motors, but it's not. You'll notice that this motor only has 2 wires. Now, notice the colors: red, hot, black, ground. Now, this type motor does go round and round and round. And this is the type motor that I would put on a wheel if I had a car and I wanted to make my car go. I would put this motor on it, because it goes round and round, and there's no set amount of distance that it has to turn. These little motors here are very powerful. This one is pretty powerful, but this one here is really powerful. This one is probably strong enough to where if you had a robot with 2 of these on it, probably you could ride on it. This is how strong these are. These are 12-volt motors, and they take a lot of juice to run them. So these motors are just called DC motors. But you'll notice the actual motor part is just this part here, and you'll notice that it's got this little top part here. In this particular case, what this top part is there's gears in here, because this motor turns pretty fast and it doesn't have a lot of power. So what we do is remember we were talking about the gears earlier? What we do is we gear it down to where this shaft turns at a fraction of the speed of the motor, but it has a lot more power. So by turning the speed down through the gears, we gain power or torque at this shaft here. Okay, and that's why these little motors are so powerful. Now there's another kind of motor, and we'll get into this later, because this gets pretty complicated. It's called a stepper motor. You see that? Stepper? I don't know if you can see that or not. And you'll notice this one has gears on top of it too. I got this this motor out of an old printer. I don't know if you can see this or not, but if I turn this, let's see, if I turn this gear here just a little bit, here's the gear coming out of the motor. If I just turn it just a little bit, you see how fast it turns the gear coming out of the motor? So in this situation, these gears here are acting the same way that these gears in this gearbox. That's what this is called, a gearbox. It's acting the same way. It's taking the power coming out of the motor and stepping the speed down so that we get a lot more power out here. But you'll notice on this motor, on this stepper motor, it has a bunch of wires coming out of it. Now the purpose of this motor, and like I say, we'll get into this later, I don't want you to worry about it. The purpose of this motor is if you need to move something precisely. Okay, like you remember my drawbot. Well, in order to draw with my drawbot, I needed to move precisely. So I use these type motors on it. And I'll come back to this later and we'll talk about it. But there's a way in here that this thing can move to a precision place, and it'll move and it'll stop. Move and stop to a precision place. And you often hear that kind of thing in a lot of robots that you may have heard before. You'll hear them go wee, 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 wee. Well, that's a stepper motor running, and we'll talk about that later. The other thing I want to talk about, back to these DC motors for a robot or a car or something like that, where it doesn't have to be precise. Let's say you've got one of these, you've got a controller, and you're going to drive your car with this controller. So it doesn't have to be precise, because when you want it to go, you'll go, and when you want it to go backwards, you'll go backwards, or right or left or whatever. Well, the way this thing works is this unit just transmits a signal. You can see the transmitter right here, the card, the Wi-Fi card. And then there's another part of it, which is this right here. And notice it's also got a card in it. And it's got a place here where you can plug, you see where it says motors? Where you can plug your motors in. And this thing will drive these motors. So if I send a signal with this to this thing, then this thing controls the motors. Okay? So I know that's a lot of stuff for you to digest, and it's a lot of stuff, and don't worry about it. Don't get stressed out, because you've got the rest of your life to learn this stuff, and by you getting these principles right now, it'll make it easier for you later on when you do really start learning about them, for you to grasp a hold of them. I'm going to open the comments at the bottom of this video. If you have any questions, just put them there, or text me, whatever you want to do, and I'll talk to you later. Good luck, and we'll see how it goes, and maybe I'll make another video soon. Take care, man. I hope you feel better soon. Bye-bye.